Hello class, my name is Ali Al-Hariri. This is a presentation on software-defined wide area network, also known by its abbreviation SD-WAN. SD-WAN is a new technology used in the design of global enterprise networks. So here's a simplified illustration of SD-WAN. Here we have multiple branches, each in a different location, possibly in a different country or continent. We also have different types of connection, as you can see from the lines and the legend. So these are three characteristics of SD-WAN. We have already talked about different types of connection and geographically dispersed sites. And here's a third characteristic, the use of overlays. Overlays are virtual networks created on top of underlays, which is a physical infrastructure, the hardware, the cables, and stuff. So here's an example of one of the connections that could be used, which is a multi-protocol label switching, or MPLS. While it is costly, it guarantees quality of service. You can contrast this type of connection with the public internet, which is more affordable but prone to congestion and delays. This reminds me of my drive to work every day actually. I could use Highway 407, which has less traffic but comes with a toll, or I could use Highway 401, which is toll free but has more traffic. So MPLS is an example of a dedicated line or protocol. By using different types of connection, SD-WAN will look at the type of data and its priority and then use the most suitable connection for it. So looking at these two pictures below, if we have a video call, for example, which is more sensitive to latency, it will have a higher priority than a text message on Microsoft Teams. So the data that has a higher priority will use the faster route and vice versa. This is how SD-WAN finds a balance between cost and performance. So here we have the four planes of SD-WAN. The data plane forwards data using the instructions from the control plane. These instructions are referred to as the network policies, quote unquote, that are based on business needs. We also have the control plane, which, as you can guess, it sends the instructions to the data plane. It acts as the brain. We can think of the control plane as the traffic control center, and the data plane as the roads and highways. The control plane formulates its instructions based on the information provided by the management plane, which we can get to next. The management plane gathers information from the data plane and the control plane and uses this information to provide a user interface to the user. So the user interface acts as a dashboard. It allows a user to monitor the entire network and make adjustments as needed. Finally, we have the orchestration plane, which assists the control plane in enforcing network policies. Just note that this plane is not always included in SD-WAN. So here we have what's called the single controller architecture. It's a common SD-WAN design, hence the term conventional. In this diagram, the network has a single controller. The limitations or disadvantages, if you will, include having a single point of failure. This means that if the controller were to fail or experience downtime, the entire network would experience disruption. After all, the data plane is relying on instructions from the control plane on how to forward data, right? So if it were to fail, the entire network wouldn't know how to forward the data. So there's less reliability. Another limitation is that such a network is not very scalable. So as the network expands, which you would assume it will, the controller will experience increasing difficulty managing the entire network. In a distributed controller architecture, also known as a decentralized controller architecture, a design that researchers are currently studying, each controller manages a part of the network. As you can see, I can see from this diagram. And this solves all the limitations mentioned in the previous slide. So now the network is more scalable. If more nodes or devices are added, then a new controller can be simply added to manage the new group of nodes or devices. If a controller were to experience downtime, then it would only affect a small portion of the network. So how could a controller know which network policy is best at a given time? Well, a promising solution is reinforcement learning, which uses machine learning. So it uses data from the entire network to learn which policy is best and then applies it to the network. So it is constantly learning and modifying policies in real time. The limitations include difficulty applying it to a large and complex network. Because you can imagine the larger and more complex a network is, the more data it will need and then has to process it to make decisions. The other limitation is exploration could lead to disruptions. Now, what I mean by exploration is trying new options, right? Because that's to test different scenarios. So for it to explore new options, it could inadvertently disrupt the network. To solve the limitation of complexity, we could use what's called a multi-agent reinforcement learning, or MARL, M-A-R-R-L. So we have multiple agents, and each agent will manage a portion of the network. It is like having multiple traffic control centers in a city, right? If you think of a city as a network, each traffic control center is a controller for a portion of the city. So as the city expands, more traffic control centers can be added. Right? So as the network increases in size, this design can manage the increased size and complexity. This design, however, does not allow the agents to communicate with each other. So each agent is fully independent and uses reinforcement learning, machine learning, to make decisions without knowledge or regard of how it can affect other portions of the network. And to improve design, researchers have came up with the MARL with network agents. So these agents now provide feedback to each other, so they can make they can make better decisions, right? And these are my references. Thank you.